In this video, we continue looking at graphing polar equations, and we're going to briefly remind you of symmetry with rectangular equations and relate that to symmetry with polar graphs as well. But we're not going to focus too much on symmetry in this particular course. We're going to mainly be focusing on using technology to help us graph. If you're not one of my students, you may use symmetry in more detail. For us, we're just going to get a brief explanation. So if you recall, symmetry with respect to the x-axis. To do that, we replace y with negative y. And if we get the equivalent equation that you started with, essentially you have symmetry with respect to the x-axis. Similar to what we have here. Here we have symmetry with respect to the polar axis. Which is essentially the x-axis. And the way we would get this is we would replace theta with negative theta. And then look at the result. If the result of the equation is the equation you started with, then you have symmetry about the polar axis here. So notice that if you reflect this point across the x-axis or polar axis, we get the same point. That's symmetry with respect to the polar axis or x-axis. Back in rectangular equations, if we wanted to talk about symmetry with respect to the y-axis, algebraically we would replace x with negative x. And if the result was an equivalent equation, we would have symmetry about the y-axis. Now in polar land, we would replace theta with pi minus theta. And if the result is an equivalent equation, we would have symmetry with respect to the y-axis, or in this case, in polar world, it would be pi halves. Again, pi halves. So if we have this point, r theta, reflected across the y-axis, or pi halves, we would have a point reflected across, again, the y-axis, or pi halves. We also had symmetry with respect to the origin back in our algebra class. And to get that, we replace x with negative x, and we replace y with negative y. And if we get an equivalent equation back, then we know we have symmetry about the origin. And now in the polar world, we're looking at symmetry with respect to the pole, which again is essentially the origin. Here we replace r with negative r and theta with pi minus theta. So you replace both of those, and if the result is an equivalent equation, then we know we have symmetry about the pole, or origin, in the rectangular system. So this one's a little bit harder to see because it's rotational symmetry, but notice that this point is down here. So once again, we're going to very briefly use symmetry on occasion, but for the most part, in this class anyway, we're going to be focusing on technology to graph polar equations. So here are the steps. We want to first solve the equation for r in terms of theta. Just like when you graph equations in the rectangular system, we need to isolate y in order to put it into the calculator. Here we need to isolate r. Next, we want to make sure the mode is in radians, and at the same time, when we're in that menu, we're going to go to the polar mode as well. And from there, we can tweak the max and min values or the x and y scale depending on the situation. For example, let's go to y equals, and notice right now I'm in the rectangular coordinate system. My settings are y equals. We want to change the mode. So we're going to go to mode. And the first thing we want to do is make sure it's in radians. My calculator by default was already in radians. If yours is in degrees, make sure we convert it to radians. And then we'll go down to function, and we want to go right to polar. Hit enter, and now we're looking at the polar system. So when we go back to y equals, notice it's now r equals instead of y. We can now type in the equation. Notice r is already by itself. That's required for graphing in polar. We have 1 plus cosine, and now we need to type in theta. Theta is a variable just like x was in the rectangular system, so we'll hit that button and notice it's going to push theta into the argument. We can close the parentheses now. And we're looking at specific settings. If you wanted to graph it from here, we could see the graph, but it's not a very pretty graph. So let's go to the window and change some settings. And notice it says theta is first. So down here we have the theta. We want theta to be from negative 2 pi to 2 pi. So negative 2 pi. Theta max will be positive 2 pi. The theta step we're going to set as 1 divided by 2 pi. So 1 divided by 2 pi. The x min, we want to go from negative 3 to positive 3. So x min is negative 3. X max is positive 3. And we want the x scale to be at 1. We can set the y scale now. The y min is negative 3. The y max is positive 3. And the y scale is at 1 already. When we hit graph, we'll see what is going to be a cardioid. It's a little skewed here because the window is rectangular and not square. If we wanted to make it look square like the rectangular system, we can hit zoom 5, zoom square. That will make the graph look a little more like an actual cardioid. So this again is using technology. We can see that it is symmetric about the polar axis. So we could talk about symmetry a little bit if we wanted to. Again, in this class, we're going to focus on technology as opposed to using symmetry in detail. And in the next video, we'll focus a little more on what the equations of cardioids look like more generically, and we'll do some more graphing.